Okay, hello. So today we've listened to a lot of really fantastic talks about functional programming and how to apply it to like everyday code, well, except for the last one. But I think that's great, and that's why we did this conference in the first place, was to like show people this side of functional programming that doesn't have to seem so academic and jargony, and you can like actually apply it, and it can all be very understandable and interesting. And this is also what I do in my own time, like when I work on Point Free or when I work with clients, and all the talks I've given at the past functional conferences all been about taking something seemingly complicated and making it seem so simple and natural that of course you could use this. And so today I'm doing the complete opposite of that. This is the least applicable practical talk I've ever given. It's really a math talk that's just hiding as a programming talk. But I think it can still be interesting for other reasons. You won't use anything in this talk in your everyday life, but I think it'll be interesting because it's very surprising. And in fact, it's pretty much not even believable that what I'm about to do is actually possible. And so I think why that's useful is that it might help you see that there's maybe something a little bit deeper to all this functional programming, math stuff, than meets the eye at first. And I think that kind of sense of awe can kind of be a pretty good guiding principle to why you can kind of trust some functional concepts, why they're maybe rooted in something a little bit deeper than other ideas that are kind of like off the cuff or off someone's whim. So with that said, what I'll be talking about, there, that looks better. Seemingly impossible Swift programs. We will implement programs in Swift that just for all intents and purposes should be impossible. It should just not be possible to implement these things. And we will implement them. And when we implement them, they will almost just boggle the mind of how could it possibly be that we could implement these things? And so I'll preface this by saying, none of this work is my original work or anything. This is all well understood ideas. There's papers and tutorials and talks and stuff like that I'll link to at the end. The only thing I'm bringing to the table here is just the presentation of this, because the papers can be very dense, and I've just tried to take a lot of time to make this into a little bit of a better story to get us to these impossible programs. All right, so we're going to start with very possible programs. Programs that are possible today. And in fact, as of Swift 4.2, there is a function called allSatisfy, which allows you to take an array and evaluate a predicate on every element of that array, and you get to say whether all the elements satisfy that predicate. So 1, 2, 3, all satisfy greater than or equal to 2, that should be false. And it is. I'll make this a little bigger. Whereas 1, 2, 3 dot all satisfy greater than or equal to 1, true. Okay, easy enough. This is obviously possible. The standard library even just comes with this function. There's another function though that is closely related. It's kind of like the dual version of it. But it doesn't come with the standard library for whatever reason, and it might be called anySatisfy, in which, given a predicate, it answers whether any element in the array satisfies that predicate. And so I'll just copy and paste an implementation real quick. Oops, sorry. Let me grab this real quick. So that's what it might look like. You just loop over the array. As soon as you find something that it satisfies, you early exit and say true. And we could use this. If I copy and paste some of the stuff, and I say anySatisfy. And maybe I'll make this 4. And now we get none are satisfied by this greater than or equal to 4, but some are satisfied by greater than or equal to 1. But this implementation isn't great because we can actually leverage all satisfy in order to define any satisfy, because there's this law known as De Morgan's law that says the negation of a conjunction is the negation of a conjunction is the disjunction of the negations, right? It just flips ands and ors and you negate stuff. If I were to write that out, if you were to negate A or B, it's the same as negating A and negating B. And using this idea, we could just very simply write this as saying not all satisfy, not P, all right? And now we still get false and true, so this is equivalent. We're just leveraging what the standard library gives us. Okay. So these are some completely possible programs. Let's now approach impossible programs. We're not yet at the impossible, but we're going to first dip our toe in getting close to it. And so what if we didn't want to answer the question that, is this predicate satisfied on every element of this array, but is this predicate satisfied on every element of a type, the entire type? All right, that sounds very impossible, but let's start small. Could we define a function on Booleans that is all satisfy? So a predicate on a Boolean is a function from Boolean to Boolean. And all this means is, well, is the predicate satisfied on true, and is it satisfied on false? This is very easy to do. Yeah, I mistyped something. So if you had a true and a false, you get, if you took Boolean, you get asked, do all Booleans, do they all satisfy that they are true? Well, that's certainly false because we have false in there. What am I missing? Oh, okay. Thanks. Okay. All right, so clearly that's false, but it would certainly be true that it's either true or it's the false value in there. All right, so that's true. All right, so we defined any satisfy on Booleans, and that should be obvious that we could do that because there's finite many values in bool. But a step further, we could say there's this weird case iterable, or I think it's weird because it's a weird name, but case iterable is a protocol that just simply says that I can give you all the values in this type. So really, we could even extend case iterable and define this function. And all it would do is call out to the all cases and then ask, do they all satisfy the predicate? All right. Let me copy and paste something to show how this might be used. So here I have an enum, and I've made it case iterable, directions, up, down, left, right. And I've asked, do they all satisfy that they're equal to up? That's obviously false. But then I defined a helper, rotate left and rotate right. So up goes to left, left to down, and so on. And for rotate right, up goes to right, and so on. With this one, what I want to ask is, do all the directions, do they all satisfy the predicate that if I take that direction and I rotate it left and then I rotate it right, I would expect I got back to where I started. All right, and that's true. All right, so we have now asked an entire type, look at all of your inhabitants, look at all your values, is this predicate satisfied for every single value? All right, still completely possible. We just did it. So now it's time to finally get to impossible programs, legitimately impossible. We're not going to implement these functions because we defined all satisfy on bool and case iterable types, but what about int? Just grab this guy. I want to define a function on int that will tell me that if a predicate is satisfied for every integer. All right, now technically the type of integers is finite. It's like very large, but it's finite. But let's just pretend it's actually infinite. Let's talk about like all integers. It would be absurd to ever think that you could definitively say this predicate is satisfied for every single integer. It just couldn't possibly. I have a fatal error here, but the kinds of things you might want to ask it are, do all integers satisfy that they are greater than or equal to 0? That should be false, but we can't even ask that. We might also ask, are all integers either even or are they odd? But we can't ask that because we can't like loop over this thing and ask. Int is just far too big. Even stranger, what if we want to do this exact same thing but with strings? Like, could we possibly do this? And no, we can't. There's infinitely many strings. We couldn't possibly ever hope to ask the string type, does every string satisfy that it is equal to the string cat? You can never do that. You might want to ask it, is every string's count greater than or equal to 0? That should be true, but we can't ask this. We can't implement these things. All right? So these things are impossible. All right? And they may seem like toy examples or weird things, but it's rooted in a pretty real thing in which if I could implement these things, then what I could do is I could define equality amongst functions like this. I could define equality that takes a function from int to int and a function from int to int. And I could answer the question, are these two functions equal? Which seems weird. And all I would have to do is take int and see, does every single integer satisfy the property that f evaluated at that integer is equal to g evaluated to that integer? Like, I would be able to do this if I could implement that all satisfy, but I can't. And in fact, this is well known for a long time now that this is just impossible. Like, not difficult, not it takes a long time, but just absolutely mathematically proven impossible. You'll never implement these functions, ever. Okay. So, all right, with that done, now that we've surveyed the possible and the impossible, now we get to look at the seemingly impossible and then show that it's not actually impossible at all. In order to do that, I'll need two types, two very simple types. The first type is bit. It has a case of 1 and a case of 0. I could use Boolean here, but I think the Booleans will get all mixed up, so I'd rather have my own type here. Enum. So I'm just making my own two-value type. All right, and then the other thing I need is something that I'll call a bit sequence, which is just a function that goes from, I'm going to use uint. It goes from uint to bit. All right, and I'm going to name this field, this function here, at index, because the idea is it's kind of like a sequence of bit values in that given any non-negative value, I get a bit. So I can say this is the 0th bit, the 1 bit, the 2 bit, and so on. It kind of is like a sequence, an infinite sequence of bit values. And I can get at a particular index. And in fact, you could probably conform this to sequence, I imagine, and this is like a sequence value. So with these types, we could very easily create values from this type, right? We could have a sequence that just simply doesn't care what index it is, and it just always returns 1. We could have one such that when we're less than 1,000, we return 0, and when the index is greater than or equal to 1,000, we return 1. So it's easy to construct these things. We can also ask these sequences, what are their values? What's the value of the y's at the index of 0? We expect that to be 0. And what's the value at the index of 2,000? We expect that to be 1. Okay. So these things, they're just infinite sequences of bits. And we can do other things. You can't concatenate two infinite sequences together because the first one never ends for you to get the second one at the end of it, but we can take one single bit and prepend it to the beginning of a sequence. And I'm going to overload addition to do this for us, in which I take a head bit, we'll call it head, and I take the tail, which is some other bit sequence, and I return a whole new bit sequence. All right? And the way I do this is, I need to return a whole new bit sequence. So let's start there. All right? And we've got some index, and we need to return a bit. Well, if the index is 0, I'm at the head, I'm going to return the new head. All right? So I put the head at the beginning. And now I need to use the tail. But what index do I use? I need to shift everything over. So I take the index and I subtract 1 so that when I'm looking at the index 1 of this new sequence, really I'm looking at 0 of the tail. All right? And so now I've been able to concatenate new heads to existing sequences. So I could take like a value of 1 and append it to our y's. And now we have a sequence that is 1 and then 1,000 zeros, and then it goes back to 1s. So this thing is like not too complicated. There's not a lot going on here, and we've got it. The fascinating thing about this type, though, the bit sequence type, it is unimaginably large. It is not only infinite, but it is uncountably infinite. You cannot put a correspondence between the values in bit sequence with the natural numbers. You can't count them. Like, you'll exhaust every single natural number that exists and still have an unconscionable number of bit sequences left to count. You can, in fact, fit infinitely many disjoint copies of the natural numbers inside the bit sequence. It is unbelievably large. It is a type of infinity larger than the natural numbers. It's big, okay? I promise. It is a very, very big set. And so that's why it may be surprising and seemingly impossible that we can define any satisfy and all satisfy on this type. Even though it's so much bigger than int and string, it's still possible. Because it turns out it's not really the infiniteness of the ints and the strings and stuff like that that's important for exhaustively searching. It's the manner in which it's infinite. And it turns out ints and strings are infinite in a way that this is not. So let's do it. Okay, we're going to implement a seemingly impossible function. And the signature would be, like all the other ones, it would be we're extending bit sequence to have this function that answers definitively in finite time, do all bit sequences satisfy this predicate. I need to make this escaping because we have closures floating. First crash. Maybe it is impossible. Oh, all right. That got me back to... All right, so let's keep going. So given a predicate on bit sequences, I will answer the question, does every bit sequence satisfy that predicate? That seems very difficult. There are infinitely many bit sequences. How could I ever hope to answer this question? I'm just going to kick the can down the road, and I'm going to appeal to the, I'm going to appeal to the any satisfy, which I have not yet implemented, because we saw that trick that I can just negate the predicate inside here and then negate the whole thing, and that would have satisfied all satisfy, and now it's my job to implement any satisfy. I need a, all right, so I've kicked the can down the road. Let's address that. So really what I am now left with defining is any satisfy, and so how can I do that? This doesn't seem any simpler to implement, and it's not, but I'm going to kick the can down the road again. Because what I'm going to really appeal to is this, let me put a fatal error in here. Because the other function I'm going to appeal to, that I didn't define in the other case, is something called find. All right, and what it does is, given a predicate on bit sequence, it will return an actual bit sequence that satisfies that predicate if it exists. If no such bit sequence exists that satisfies the predicate, it'll return me some bit sequence. I won't even know what it is, but that detail's not going to be important, as you'll see in a moment. All right? Because if I had that, what I would do is I would ask myself to find the bit sequence that satisfies that predicate, and then just plug it right back into the predicate. Because if I found a bit sequence that satisfied it, I would plug it into P, and I would get true. If no such bit sequence existed, I would get some kind of gibberish sequence I don't really care about, and I'd plug that into P, and I would get false, because it does not satisfy the predicate. All right? So this is just a little twist, a little trick we're employing to kick the can down a little bit farther. All right? And now I've boiled it all down to this function, the find function. But this doesn't seem any easier. How can we possibly hope to now find in the infinite vastness of the bit sequence type a bit sequence that satisfies a predicate? Turns out we can actually do this recursively. We can actually think about it recursively and cook up this function. Just make sure I'm not skipping anything. My notes got reset. Oh, I was missing. And that brings us to achieving the seemingly impossible. All that stuff that was above was supposed to go down here, but we're in the process of achieving the seemingly impossible. All right. So we're going to define this function, and we're going to do it recursively. All right, here we go. So what we can do is we can break it down into a recursive problem in which we kind of peel away one layer of the bit sequence and try to see if we can find something that's satisfied on the tail, and then if we do find that, reassemble them and then get something that will be satisfied on the whole. So what we do is we ask, well, I mean, is there any bit sequence that satisfies that if I peeled off a 0, that then I'm satisfied by the predicate? All right? So if we were able to do this, then what we... Are there any Apple employees in the audience? All right. If I were able to do this, sorry, let me get my notes in order again. Okay. So if I were able to do this, then I have successfully been able to peel out the 0, and then I will then go in and find that bit sequence that satisfies that inductive property I was just describing. All right? And otherwise, that means I couldn't, by peeling off a 0, I was not able to do this. So let's try peeling off a 1. So I will then try peeling off a 1 and then finding the rest of the sequence in which I peel off a 1 and then construct the rest. Got a capital S here. Okay. All right. We just implemented, supposedly, an impossible program. But there's a pretty significant problem. And in fact, I think Swift is actually warning us right now about it. And I think it was in Swift maybe 4.1 or something that they introduced this very interesting warning that will tell you in which all paths of your program are just calling itself. And so this thing will never terminate. And in fact, there's no reason to think that this thing would ever terminate, because not only is find calling itself, but find also calls any satisfy, and then any satisfy just immediately calls find. So there's no way this could ever terminate. So we actually haven't accomplished anything, because of course you can write non-terminating functions that do whatever you want. Like, they don't terminate. You don't know what they're going to produce. But amazingly, we can actually fix this. And it's not that big of a deal, because you'll see that we're always like peeling off the 0 and then prepending it to the rest of the array. Now, this is a very eager operation. And what we want to do is we want to introduce some laziness so that it turns out that if we introduce some laziness, we will do as much work as needed to get the job done, and then we'll just kill it. And it turns out that is how this entire trick works. That's why bit sequences are so unique. And so I'm going to introduce a little bit of laziness into our concatenation operator, in which there are going to be times in which I don't need the tail at the moment of concatenating, that I will get like truncation at an earlier moment. And the way you do this in Swift is to introduce an auto closure. All right, and then because we're using this then in a closure also, I think this needs to be an escaping auto closure. And then you just have to do this. So that was very simple. I think it's compiling. And now these errors are just that now we need to introduce more escaping stuff. So I'll do that. And now these have to be escaping. So we just got a lot more escaping going on. But I think once we do this, what we'll find is that not only did it compile, but also that warning went away. No longer can Swift prove that all paths in the function are just calling itself. And it's because we introduced some laziness so that we get some later moments to just kill it. All right, but this still is never going to terminate, because any satisfy here is just immediately calling find. So these two things are just going to bop between each other. That's never going to execute. We need some further laziness in here. All right, and so what we can do is just invoke find lazy. We need to kind of wrap it up in a closure somehow. And how will we do that? Well, we know what we're trying to search for, what we're trying to find is a bit sequence, so we can do that. So we're at some index in this bit sequence. What is the value at this index? Well, inside here, we will then do the find and then get at that index that we're looking at. So we just wrapped find up in a whole new closure to introduce some laziness. And then once we found it, we'll plug it in to the predicate. All right? All right, so I think this is compiling. And now we have achieved the seemingly impossible, and like legitimately this time. I mean, you would need to do a lot more work in order to mathematically prove that this always terminates. It is possible, it can be done, but we've done it. And the only way to really feel like we've done that is to actually take it for a spin. So let's do that. So I'll do something silly in which I'm going to find a bit sequence satisfying some predicate. And this is the predicate. I'm going to find the bit sequence that satisfies that at index 0, we're 1. At index 2, we're 1. At index 4, we're 1. 6 and 8, we're 1. No other indices matter. I don't care if there are zeros and ones anywhere else. I just want to find that one sequence. And there's many sequences. I want to find some sequence that satisfies this. So let's see if it worked. So at subsequence, I'll ask at the index, what are you? We're 1. Like we demanded from this predicate. Let me just copy a whole bunch of these. 2, 3. You can see it doing some work as I type these. Sorry. Maybe I'll just copy and paste what I was going to do. Okay. You can see it's taking some time, and it's doing a lot of computation up there. But I have plucked out of thin air some bit sequence that satisfies this predicate. The find doesn't know what predicate I'm feeding it. I can give it any predicate, and it is plucking out of thin air a sequence in this infinite vast space, an infinity that is just unconscionable, unimaginable. Our feeble human minds can't even comprehend it. We can come up with tools in order to like do things with it, but we can't actually comprehend it. And we've done it because this sequence is indeed 1 on 0, 2, 4, 6, 8, and then it's 0 everywhere else, but it could be whatever. We didn't care what it did on all those other values. And so we've seemingly accomplished the impossible. So let's keep on taking it for a spin. Oh, well, yeah, I guess I should comment. It is interesting how many times it's hitting these. Like, it's doing a lot of work in order to find this. It's still finite. It's still a lot less than infinity, but it's hitting it quite a bit. And because it does a decent amount of work, I'll just comment out all of this so it's not bogging down Xcode. All right. So maybe we should ask some other questions of our bit sequence, like the any satisfy and all satisfy. So I could ask it, for example, does any bit sequence satisfy the property, or do all bit sequences satisfy the property that at index 0, the value is 0? And of course, that's false. Does any bit sequence, or do all bit sequence satisfy the property that at 0, we're 0, or at 1, we're 1? That's false. You can construct bit sequences that do not satisfy that. But do all bit sequences satisfy the property that at index 0, you're 0, or at index 0, you're 1? Of course, that's true. 0 and 1 are the only bit values we have. And then, does any bit sequence satisfy that the index at 4 is equal to the index at 8? It took 3,800 times of running this code to verify it, but it definitively, exhaustively verified that, yes, there is some sequence out there that satisfies that the index at 4 is equal to the index at 8. Okay. So it's pretty interesting. And it gets more interesting when you think about that equality operator we had, because we couldn't define equality of functions from int to int. Yet, now that we have all satisfy, we can define equality between functions on bit sequences, even though bit sequences are just absurdly large. I'm going to comment out these lines since they're doing a lot of work. So let's take this for a spin. I have a couple of silly functions here. One in which a bit sequence that we just always return 1, and a bit sequence in which we just always return 2. Of course, const 1 is equal to const 2. Const 2 is equal to const 2. But const 1 is not equal to const 2, obviously, but it did it. And in fact, it did it without very much work. It only called these functions 4 times. So it seems like it kind of just figured it out pretty quickly. Let's try something more complicated. In order to do a more complicated one, I need to be able to play with bit values a little bit more. So if I have a way of just kind of getting a uint out of a bit value, like converting 1 to 1, 0 to 0, I can construct something a little bit more complicated. For example, let's take a look at these two functions. All right, so this is a function on bit sequences that multiplies the sequence at 1 with the sequence at 2, and then one that adds the sequence at 1 to the sequence at 2. And what do we expect? Well, f should certainly be equal to f. That's true. And g should certainly be equal to g. But f should not be necessarily equal to g because in the bit world, right, 0 plus 1 is 1, yet 0 times 1 is 0. So we would expect that this is false. And it is false. And it called it 225 times in order to definitively, exhaustively search all of infinite space and figure that out. All right, let's mess with it a little bit more because these functions are kind of obviously not equal to each other. Let's take something that's maybe not as obvious. I'll paste in 2 more. All right, so h is one in which we switch on the index at 1 and 2. And if it's a 0 in anything or in anything in 0, I return 0. And if it's a 1 in something else or something else in 1, I return that something else. Maybe you see it as this being equal to one of the others, but let's just check. Is h equal to f? Okay, it is. Is h equal to g? It's not, as we'd expect. But what about this k1? Now we're taking the index at 2, adding 142 to it, taking the index at 1, adding 766 to it, adding those together, modulo by 4, and then dividing by 2. Like, who knows if those are equal? But let's ask. Is k equal to f? It is, weirdly. And is k equal to g, and is k equal to h? Is that what I expect? No. Uh-oh. We're going to have to zoom past that. Let me run in my playground over here. All right, we zoomed by. So, I don't know about you, but I find all this very surprising. And when I first read this paper, it just didn't feel believable, to read that this was possible, and I had to implement it myself to really believe it. And amazingly, you can just implement it in Swift. It's pretty easy, except for the laziness. The paper originally wrote it in probably Haskell or something, or I don't remember, where you just don't even worry about laziness. It flowed very naturally, but once you get over those humps, you see it. And so then the question becomes, this is where I'll just tell as short of a story as I can really quick, and I'll wrap up, of now that we've achieved this seemingly impossible thing, how could we ever possibly explain it? What is the idea that is connecting reality, what we can actually prove, to this seemingly impossible thing? And what it has to do with, surprisingly, is a topic in math known as topology, very surprising. And the reason it has to do with topology is because, and these are results that have been known since the mid-1800s to late 1800s, and the reason it has to do with topology is because topology is the study of spaces in which you can very abstractly talk about how points are close to each other. Very, very abstract. If you look at the definition of a topological space, you won't even see that there's any notion of closeness there, but it's there. And just like in programming, it's very important to know about functions between things. That kind of reveals a lot of relationships. You want to know about functions between topological spaces, and those are known as continuous functions, in which they preserve the closeness of points in some way. All right? And so then once you know the objects you're studying and the things that map between them, then you want to know about what subsets of those have nicer properties than the wild world of continuous functions and topological spaces, because it turns out there's lots of wild things. One such nice thing is a compact space. A compact space of a topological space is one that, although not finite, has a lot of finite properties about it. That should maybe tickle something in the back of your mind with that bit sequence type. It was certainly not finite, yet we were able to exhaustively search it. And then continuous functions, there's a subset of them known as uniformly continuous, which not only do you get to say that close points map to close points, not only do they preserve the closeness of points, but the manner in which the close points map around is uniform across the entire space. No matter where you are, the closeness, the measure of closeness is always the same. All right? And so then it turns out that in computation, in this weird connection between programs and types and proofs and stuff like that, that every function is continuous. There is no such thing as a discontinuous function. And continuous functions on compact spaces are uniformly continuous. And all of that is to say that bit sequence is a compact space for very clear reasons, although there's no reason for you to believe me, but it is a compact space. It has finite properties, even though it is certainly not finite. And all the functions we defined on our bit sequences are continuous and therefore are uniformly continuous. And therefore, what you get from this uniformly continuous property is that you get to search for predicates to be satisfied on a suitably large finite set, and as soon as you do that, it is satisfied everywhere. It is such a strong property that you just get to search for a finite amount of time, and if you verify it in that finite amount of time, you actually have it for all of the infinite space. And those are all the theorems. That's a crash course in topology that gets you to understanding this result, that somehow the topology, the compactness, the uniform continuity, all this stuff gets to the point where you get to write a program that should be absolutely impossible, but is possible. And that's the talk. Yeah, thanks. Okay. Any questions? Yeah. I don't know who said that, but no, I have not. was a question about the Goldbach conjecture. Yes? I was expecting a false there, and I'm scared to go back and look, but I'll make a note of it when the video's up, and I'll correct whatever code I messed up. We certainly didn't discover a problem in the method. It was a problem probably in my live coding. So you think I should scroll up and look at it? Thanks for giving me the confidence to do this. Ah, yes, okay, it's true. Thank you. All right, this is good. Okay, now I feel good. Yeah. Thank you. All right. Yeah, I thought we had achieved, I thought we had gone back to being impossible, and now we're back to possible. All right, any other questions? Over here. Yeah, for sure. So it turns out it's actually equivalent to a space known as the Cantor set, which is like a very nice tool to use. Like you can teach like a kid this kind of mathematical object in which you take the unit interval and you remove the middle third from it. And then from the two intervals that are left, remove the middle thirds of those. And then the intervals that are left there, the thirds of those keep on going, and you get this almost fractal-like set sitting there inside the unit interval. And so right there you see it at least has a finiteness about it in that it's contained in the unit interval, but there can still be non-compact things in the unit interval, but it just turns out the way in which all the points cluster together gives it the finiteness property to it. So that's a very hand-wavy way in which you can see there is a finite aspect to it. And also the Cantor set and the bit sequence set, they're also equal to just the real numbers on the unit line whose ternary decimal expression, or ternary, if you wrote it out in like ternary, it's all the numbers that don't have the number 1 in its expansion. So like 0.0, 0.002, all 0.202, all of those are in this set. Yeah. Yeah.
So you can also represent numbers as the sequence of powers of primes, right?
Yeah.
So that would be a bit sequence.
Yeah.
Still have these nice properties, or are you getting into like danger land?
So as long as you're staying in compact world, you're good, and it's surprising how resilient compactness can be. In fact, you can take a infinite product of compact things and still be compact. So I don't know, I can't quite off the top of my head say how this relates to your thing, but it is very resilient, although also fragile. Like it can be also surprising how sometimes you leave compact world and you didn't mean to. But also I then think I need to add the further caveat that the proof of the infinite product of compact things being compact uses the axiom of choice, in which now we're outside the world of constructive math. Like all the stuff I'm saying is there's like a type of math in which you have to forget a couple of axioms because they're not representable in computers, essentially, and you have to redo all of math when you do that. But yeah, that's the answer. In the back? As a subset of the bit sequence.
Yeah. But if you, can we sort of like kind of do the functions, like the all satisfy on these about as.
So no, the only, I guess I haven't been repeating the question. So this is a question, I think, about asking about, is there anything we can salvage from this to try to recover all these properties for integers or subsets of integers or anything like that, maybe roughly? And no, definitively not. The only compact subsets of the integers are the finite integers, and which, of course, you can exhaustively search those, which I did at the beginning. So 100% math says you will never exhaustively search any subset of the integers that is not finite. So is this useful for anything? I mean, even the people who wrote the paper, and I should scroll down a little bit more. So here, I'll post all this stuff at some point. Here's some nice, I'll keep going. So I think the first paper is the original one. A follow-up, like longer discussion is the second paper. The third one is just a blog post that is like far more approachable than anything else, but I tried to like make it even nicer. And then the last one is like just slides of a talk that this guy gave. But even he says it's like it's very experimental to know what the applications could be. As far as he could possibly even imagine, maybe like proof, like program verification, like somehow being able to search a finite set in finite time is certainly powerful. And so maybe if you get to search out like the fuzz testing, rather than hammering it with all types of random values, what if you could just simply exhaustively search the infinite space of possible things you could plug in? Yeah. I think that's very experimental. I don't think anyone's done it. Okay, I think we should, oh, okay.
The topology is the one you don't know what to use it for?
No. This application of topology, the exhaustive searching of like the implementing the impossible program on bit sequence. Yeah. I mean, topology's got lots of applications. Yeah.